this. All right, let's go through a quick revision of what we learned last week. Basically, the first thing we learned about is thermal expansion, right? Like I've mentioned over and over again, thermal expansion occurs because the particles gain energy, vibrate at a greater space, and thus expands in all different positions, right? We know for a fact that heat expands and cold is definitely going to contract, right? And these are the applications we talked about last week. Then after that, we also talked about how come a thermometer, the indicator drops a little bit before it rises to the top. Is because what's happening is when you place this thermometer into the hot water here, right? If you place it into hot water here, the heat actually reaches the glass first, right? And when it reaches the glass first, it causes the glass bulb to expand a little bit. When it causes the glass bulb to expand a little bit, the liquid levels will drop a little bit. Then after that, when the heat penetrates through the glass to the liquid here, what's going to happen is the indicator will shoot up to the proper temperatures here, right? So, and after that, we also talked about the calibration of a thermometer, right? In order to calibrate a thermometer, I mentioned that first and foremost, we must use the linear expanding liquids. This is always asked in your IGCSEs. Linear expanding liquids are always going to be alcohol and mercury, guys. They expand linearly with temperature change, right? Then after that, the calibration process involves the 0 and 100 degrees Celsius. That is usually melting of pure water ice, and then boiling of pure water, right? These two are known as the fixed points because at these two temperatures, we know for sure this is what's going to happen during these temperatures, right? Then after that, we also talked about this part here, the sensitivity, linearity, responsiveness, and range. Last week, right? Basically, sensitivity is the ability to measure small changes. Today, if I have a sensitive thermometer, it will have a lot of readings in between, right? If I have a non-sensitive thermometer, it will be like 0, 10, 20, 30, 40, 50, and so on already, right? So the best way to improve the sensitivity of a thermometer is always using narrower tubes, right? This narrower tube means to say the same amount of liquid can push up further, which is something we want. Or we want to use a larger glass bulb here. A larger glass bulb means to say there's more liquid that can be pushed up into the thermometer. Very important, always asked in your IGCSEs, guys. Now, after that, we also talked about the difference between range and sensitivity. Like I mentioned last week, if today you improve the sensitivity, the range for sure drops. If you improve the range, the sensitivity for sure drops, because range and sensitivity, they are always opposites of each other, right? And if they're opposites of each other, one improves, then the other one must deprove, if there's such a word. And if you look at the improvement of the range, it will be the exact opposite of the sensitivity. You have to keep this in mind, guys. You see here, this one used narrower tube, right? This one wants a greater diameter of the capillary tube, right? Then this one here use a larger glass bulb. This one here, they want to use a smaller volume bulb, guys. So indicating that they are the opposites, right? Then from here, linearity and responsiveness is, like I mentioned just now, linearity is linear expanding liquids. That's why they have the readings with equal spacing between each other, all right? Usually we use alcohol and mercury. Then the responsiveness is basically how fast you can react to the change in temperature, right? Of course, the best way to improve the responsiveness is to use a thinner glass bulb, because when you use a thinner glass bulb, the heat does not need to penetrate through so much glass and reach the liquid much faster, guys. So this is what we mean by thinner glass bulb. So then, yeah, this is just a table that I tabulated for you to see what changes improves what and what changes doesn't do anything, right? Then the final thing we learned before we ended class was basically a thermocouple, right? A thermocouple is basically a steroid-induced thermometer, right? Basically, it can have super large range and they have super rapid responses. In your IGCSEs, they love to ask you this. They'll ask you what are the main advantages of a thermocouple thermometer, which you are going to answer, it has super large range, it has super fast responsiveness. Why? Because it uses metal to measure the difference in temperature, guys. So last week we talked about how a thermocouple works, right? Anyone here don't remember how a thermocouple works, guys? Anyone here need me to give you a quick recap for the thermocouple? If you can remember everything, then let's look at this past year paper here from your IGCSEs. Okay, let's go through it all together, guys. Maybe I'll give you some time to attempt this first later on. So if you look at this question here, what do they want from you? First and foremost, they say that figure 4.1 shows a thermocouple. You have a voltmeter, metal B, metal A, ice cubes, and hot water here. Obviously, this is the cold junction, and this is going to be the hot junction, right? It's going to be cold junction, this is going to be the hot junction here. They say that during this scenario where it's 0 to 100 degrees, which is yet again the calibration process, it says that the voltmeter reading is 5.4 millivolts. Okay, so right now I understand that 5.4 millivolts causes a difference of 100 degrees Celsius from the cold to the hot junction. Okay, very important. This is my calibrated understanding. First and foremost, they ask you, state the name of this type of thermometer. Obviously, it's known as a thermocouple thermometer. Thermocouple thermometer. Right. Nothing to explain there, right? Then after that, this is the part where it gets interesting. In the next part here, it says that figure 4.2 shows the same thermocouple used to measure the temperature of liquid X. Right now, I don't know what's the temperature of liquid X, but looking at the question, it says that with this setup in figure 4.2, the voltmeter right now reads 1.7 millivolts. Okay, it reads 1.7 millivolts. And they asked me to calculate the temperature here. What will the temperature be given that the calibration is 5.4 millivolts is equals to 100 degrees Celsius. Can all of you guys try to attempt this question? I'll give you maybe 5 minutes to attempt this. Can you do this now? And let me know if you can find the answer. Refer to the notes that you written down from last week, guys. Everyone, attempt this now. Send me your answers. Wait, who here has absolutely no idea what to do? Are you guys stuck or something?
Mr.
Sorry?
Gabriel,
Yep.
can you like refresh the how to calculate the thermocouple?
Sure. Let's go through it one more time, everyone. By the way, Leha, have you learned this from school already?
Oh, I haven't.
Oh, yeah, then yeah, you might be a bit confused here. Okay, guys, now listen up. You may want to copy this down as well, guys. Usually when we play with thermocouples, right, first things first is we want to go through the calibration process, right? If we want to go through the calibration process, first and foremost, we'll have the, I'll use a different color. We'll have the galvanometer, right? That will be connected to metal X. That will be in the hot junction and the cold junction here, along with metal Y that will be connected to the hot and cold junction as well. Today, if we want to go through the calibration process, first and foremost, we'll always dip it into the fixed points, right? Fixed points being the 100 degrees Celsius and also the 0 degrees Celsius here. Let's say today, if we dip these two metals in, right, what happens is the galvanometer, they give me a reading of, let's just say for ease of calculation, 0.1 amperes of reading, right? If it gives me 0.1 amperes of reading, this is my calibrated understanding, right? I know that every 0.1 amperes difference in the galvanometer gives me a reading of 100 degrees Celsius difference between the hot and the cold junction. From the hot to the cold should be a difference of 100 degrees Celsius. Today, if let's say I want to measure something that is super hot, I don't know how hot it is. Usually what we'll do is we'll put the cold junction in the same fixed point now, which is going to be the 0 degrees Celsius. We want to measure something that is damn cold, I don't know, damn hot, I don't know how hot it is. I don't know, right? I'm looking for it. But when I place these two metals into the hot junction, what happens is the galvanometer gives me a reading of 0.5 amperes. From here, if let's say it was 0.5 amperes, how hot will the hot junction be? $500. Good. It is supposed to be 500 degrees Celsius because, like I mentioned just now, this calibration process tells me that the difference between the hot to the cold junction should be 500, right? Because if 0.1 amperes is 100 degrees, then 0.5 amperes should be 500 degrees Celsius. Since this starts off with 0, I just need to plus 500 to be here only, am I right? What if the question gives you something different, right? Like for example, right now, the question, they did not start from the fixed points, right? Let's say right now, I start from 50 degrees Celsius, okay? If let's say it is 50 degrees Celsius, and let's say the ampere reading right now is 0.2 amperes, how much will the hot junction be? How much will the hot junction be? Okay, for those who do not know what the hot junction, how much will the hot junction be, right? First and foremost, you ask yourself, if this gives you a reading of 0.2 amperes, then what should the temperature difference be? 0.1 represents 100 degrees Celsius difference, right? Then 0.2 is obviously supposed to give you 200 degrees Celsius difference, right? Yes, correct. If it gives you 200 degrees Celsius difference from the hot junction to the cold junction is 200 degrees Celsius, then obviously you plus the 200, which will give you 250 degrees Celsius difference, right? Sorry, 250 degrees Celsius reading, because from the cold junction to the hot junction, the difference in temperature should be 200 ma, right? Then from here, if you can understand this, and anyone don't understand this, by the way. Anyone don't understand this, this is actually very important. You better say something if you don't understand. From here, if let's say you understand this, right, then let's say right now I want to measure something that is damn cold. I don't know how cold it is, but once again, I use the reference point of 100 degrees Celsius here. Right now, my galvanometer reading gives me a reading of 0.3 amperes. If it gives me 0.3 amperes, how cold will it be? How cold will it be, guys? First and foremost, you ask yourself, what's the difference in temperature between the hot and cold junction? Wait, how cold will it be? Wait, faster. Wait. Okay, first and foremost, tell me what's the difference in temperature between the hot and cold junction if I have a 0.3 ampere reading? $200. Are you sure it's 200? 0.2 amperes is already 200. Oh. Yes, it'll be negative 200, right? Why? Why will it be negative 200? Because first and foremost, this galvanometer reading gives me a 0.3 amperes difference reading, right? If it gives me a 0.3 amperes reading, it means to say that the difference in temperature between the hot and the cold junction is 300 degrees Celsius, right? If the difference between here to here is 300 degrees Celsius, now, obviously, you need to have 100 minus your 300, which is going to give you negative 200 degrees Celsius, right? Very good, Raj. It seems like you are the only one that understands, though. Nadia and Leha, do you understand what I'm talking about or not, guys? You're supposed to find out what's the difference in temperature first, then only you jump it from here to here. You guys understand or not?
Yeah.
Okay. So from here, if you can understand this here, let me take a screenshot. If you can understand this here, then looking at this question, look here, this is essentially what we learned about, right? First and foremost, they ask you that, they tell us that 100 degrees Celsius difference is 5.4 millivolts. Then right now, it tells me that it's 1.7 millivolts. First and foremost, tell me what is the difference in temperature between the hot and cold junction. How do I find that? What do I do? Wow, 540. How can it be 540? 1.4, 5.4 is going to be 100 degrees Celsius. 1.7. Hey, Raj, you cannot follow the previous example, because the previous example, it was two different metals. Right now, this example, they give you two different metals as well. And because of that, you must follow their calibration process. You get what I mean? This here, the 5.4 millivolts tells you that the difference between the temperature here is 100 degrees Celsius. Right now, if 5.4 millivolts represents 100 degrees Celsius, then how much will it be if it's 1.7? You know what's going to happen, right? If let's say it's a 200 degrees Celsius difference, if it's a 200 degrees Celsius difference, the reading in the voltmeter will be 10.8, And if let's say it's a 400 degrees Celsius difference, right, the reading in the voltmeter will give me like 21.6 millivolts, So right now, if the millivolts is 1.7, then how much will the difference in temperature be? How am I supposed to do this? I'll give you guys 2 more minutes, then after I'll have to explain this already because it's taking too long already. Try to attempt this. If 5.4 represents 100 degrees Celsius, then 1.7 represents how much? It's definitely going to be smaller, right? Because the voltage is smaller, right? Means that the difference in temperature should be smaller as well. Oh, very good, Raj. That is the correct answer. Good. How am I supposed to find? Oh, very good, Nadia. You found the answer as well. Very good. It is supposed to be somewhere around 31.5 degrees Celsius. How did you guys get that? You can do it using the ratio method lah. If 5.4 represents 100 degrees Celsius, 5.4 divided by 1.7 should be equals to 100 degrees Celsius divided by your X amount, right? From here, it's just a matter of pressing everything into your calculator or playing with your numbers, right? 5.4 divided by 1.7 will give you how much? 5.4 divided by 1.7 will give you 3.17 something. So you take the 100, is 3.18 lah, right? You take the 100 and you divide the exact same number, you'll get 31.5 degrees Celsius. Excellent job, Nadia and Raj. You guys found the answer here. So if, let's say, right, the difference in temperature between the hot and cold junction is supposed to be 31.5 degrees Celsius, how much should this liquid be? One more step to find your final answer, guys. How much will the liquid be? 51. Excellent job, Nadia. Very good. It is supposed to be 51.5 degrees Celsius because from the cold junction to the hot junction is a difference of 31.5 ma. So obviously the hot junction here is going to be 51.5 degrees Celsius. 51.5 degrees Celsius. Excellent job. Let me screenshot this as well. Everyone understand this or not? Guys, anyone confused on this part? Leha and Raj, you guys understand now the final answer? Yeah. Okay. Then moving on to the homework. Yeah, it's you're supposed to round up, guys. By the way, just for the benefit of the new students here, guys, I mentioned this before. All your answers in the paper should only be 3 significant figures, meaning to say if you found your answer to be 51.48, right? This is 4 significant figures, right? They will actually minus your mark. So you can only leave all the answers in this dotted line here as 3 significant figures. I've said this many, many times. Please make sure you remember it. Okay. Then moving back here to the exercises, guys, this is supposed to be your homework, guys. I do hope you have done the homework because, you know, if you don't do the homework, you'll definitely not improve. I think I've said this 1,000 times before. Please don't just watch the show. It's different from outputting and inputting, guys. All right, so let's not waste any more time. Let's go through the answers from the homework real quick. If you look at the first part here, the first question in your homework, this says that figure 4.1 shows the device used as a thermocouple thermometer. You have meter Z here, you have material X, and you have material Y. Obviously, looking at here, this is obviously the hot and cold junction. This is your galvanometer, and this is your metal X, and this is your metal Y here. So looking at the question, they say that in the table, put 3 ticks against the correct statement about the thermocouple thermometer here, right? So first and foremost, they ask you meter C, does it measure energy? No, a galvanometer can measure voltage or current only, so this is not it. Potential difference, this is it. Potential difference is just another way to say voltage, guys. So for those who do not know, you can write a small little V here to indicate that potential difference is voltage as well. Power is definitely not it, right? Because galvanometers do not measure power. Material X and material Y are of different materials. Definitely true, right? Like I keep saying in previous week, I said that the galvanometer must have two different metals. Metal X and Y are the same material. Definitely not true. Metal X and Y are electroconductors. Definitely lah. They must be metals, right? If not, insulators will not allow current to flow through at all, guys. So your answer should be potential difference, same material, and also electrical conductor here. I think most of you guys should not have this question wrong, right? Then after that, the next question here, it says the 3 wires and the metal are made to construct a thermocouple for measuring the surface temperature of a pipe carrying hot liquids on figure 7.1. Copper wire and constantan wire are used in the construction of the thermocouple. State which metal might be used for wire 1, 2, 3, right? So if I look at this diagram here, this is just another confusing way to look at a thermocouple. They already say that this is the cold junction and this is the hot junction, right? If this is the cold junction and this is hot junction, that means to say this is one metal and this should be another metal, right? So if I'm given copper and constantan, then I obviously have to say that wire 1 and wire 2 are copper, right? Copper and copper here. Then obviously wire 3 here is going to be constantan, right? But it doesn't necessarily have to be copper, constantan, guys. Like here, I written the answer as copper, constantan, right? It could also be constantan, copper. It doesn't matter which way you arrange it, as long as you say that the 2 wires are different. So you have to understand that these 2 are one wire and this one is another wire here, because 2 different wires will touch the 2 different junctions. Very important. Okay. And after that, they ask you state the type of meter used here, right? You can obviously write galvanometer as your answer, right? You could also say millivoltmeter or milliammeter. Beyond that, any other, it's a bit gray already, right? Some students, they'll write voltmeter here or ammeter here. That is definitely not true, guys. You always remember that a thermocouple, right, they can only measure very small changes in voltage and current, right? So it needs to be either a galvanometer, which can measure small voltages and small current, or it could be a millivoltmeter or a milliammeter, which can also measure small voltages and small current. So if you've written down either galvanometer, millivoltmeter, or milliammeter is acceptable, I definitely recommend writing galvanometer as your answer. And then finally, the last part here, they ask you state one particular advantage of a thermocouple for measuring temperature. Like I mentioned, there's only 2 standard answers, right? It is either rapid response or large range. You can see there are a lot of thousands of different answers as well, right? But I do not recommend writing down or memorizing any of it, right? Because these 2 answers are rapid response and large range are always in the mark scheme, guys. So I know for a fact that these 2 are definitely standard answers here. Okay, just make sure you write rapid response or large range, which is in line with the notes here, right? Rapid response or large range. Anyone is acceptable because it's only 1 mark here. Okay. Anyone's got any questions with this part here? Anyone need me to clarify anything before I move on to the next part? Mm-hmm. 100% absorption rate, as usual again. Then moving on to the next part here. Yeah, moving on to this next part here, right? They basically say, what do they want from you? First and foremost, they say that equal volumes of gas held at constant pressure, a liquid and a solid undergoes the same temperature rise. Both of them are subjected to heating. State which 3 solid, liquid, or gas expands the most? Obviously, if you want to think back about which one expands the most, is going to be the fact that their forces of attraction are either strong or weak, right? Today, I know for a fact that gases have the least forces of attraction, meaning to say it's very easy to supply energy to the molecules and pull them apart, right? So obviously, the one that expands the most is going to be gas. Whereas the ones that expand the least is definitely going to be solid, because solid particles are held together with very strong forces of attraction, right? If they are held together with very strong forces of attraction, it's very hard for them to provide energy and separate away. It will always go back, right? Explain why the pressure of a gas must be kept constant for this comparison. Today, I know for a fact that the pressure of the gas must be kept constant because I'm playing with the temperature and volume, right? Today, if I'm playing with temperature and volume, the third component, which is the pressure, must be kept constant so that I have fair comparison, because pressure affects the temperature as well. So you're going to say that pressure is kept constant. Pressure is kept constant for fair comparison. Okay, you're going to say something like that, right? Yeah, because change in gas causes the change. Yeah, you could also say that change in pressure changes the volume or temperature as well. Change in affects the volume. Something like that. Okay. Right. Write this down real quick. Okay, then after that, moving on. If you look at the next part here, it says that figure 5.1 shows an alcohol thermometer. State two properties of alcohol which makes it suitable in this thermometer here. Now, if you look at this thermometer, you'll notice that it starts off with negative 10 degrees Celsius and it goes all the way until 70 degrees Celsius. Now, first and foremost, I mentioned this before, right? You definitely cannot put any other thing besides alcohol or mercury in it because they are the only linear expanding liquids, right? So first and foremost, you're going to say, alcohol expands linearly with change in temperature, right? This is definitely your first answer here. And the second reason why you put alcohol here is because you look here, it starts off with negative 10 degrees Celsius, right? Then if you put water in here, obviously water would have frozen by here, right, at the 0 degrees Celsius mark, meaning to say it would not be able to read all the way until negative 10, right? So for me, the second answer will be alcohol remains liquid even at negative 10 degrees Celsius. You'll write something like that, okay? Alcohol expands linearly for sure. That is a standard answer. And looking at the question here, since it starts with negative 10 degrees Celsius, you can say that alcohol remains liquid even at negative 10 degrees Celsius, right? Which is probably in line with the mark scheme here. You see here, it says expands uniformly for sure, linear expansion, remains liquid over the required range, expands more than the glass, has reasonably low specific capacity, has lower freezing point than mercury. Either one, anything that's logical is going to be acceptable for sure, guys. All right, so write down anything that's logical. It will still give you your marks here. Okay, then after that, moving on to the next part here. Look at this. This is a super standard question. State two changes to the design of the thermometer which would make it more sensitive. if you had a look at the notes that I've given you, obviously the two ways to improve the sensitivity is to, number one, decrease the diameter of the capillary tube, right? We want the capillary tube to be smaller so that the liquid is able to push up more, right? And the second one is obviously to increase the volume of the glass bulb, right? If I increase the volume of the glass bulb, obviously it's going to be able to contain more liquid, so it's able to shoot up even further because there's more liquid to shoot up the thermometer, right? So that is the main answers in improving the sensitivity. Super important. Always ask year in, year out. It's the same question every day, guys. Okay, then finally explain why it is an advantage for the glass surrounding the alcohol in the bulb of the thermometer to be very thin. Why would I want the glass bulb to be very thin? Like I mentioned just now, the glass bulb affects the responsiveness. Today, if you have very thin glass bulb, obviously what's going to happen is the thermometer is able to respond faster to temperature change. Able to respond faster to temperature change. Or you could say improves the responsiveness or anything that is logical. And obviously, you still get your marks. Okay. Anyone's got any questions with this part here? I can say narrow tube. Yeah, that's acceptable. Narrow tube is essentially a smaller diameter in the capillary tube. Definitely acceptable as well. Okay. Then moving on to the final question here. Actually, this final question is a bit weird. I think I should remove it for the next batch already. Maybe when I do my revision. If you look at this next question here, the final question, figure 1.1 shows a liquid in glass thermometer. In the process of making the thermometer, the scale divisions were spaced equally. Okay, they say that the scale divisions here are spaced equally. And obviously, they ask you what assumption is made about the liquid. There is only one standard assumption that we make about the liquid, which is that the liquid expands linearly with change in temperature here, right? This is a super standard question with a super standard answer. Just make sure you understand what I've been talking about. Okay. Then the next part here, this is suggest two changes to the thermometer that would require the spacing of the scale division to be larger here. Today, if I want the scale division to be larger here, it basically means to say I want to have more reading between each and every one of the scales. So instead of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? I want it to be 0, 0.1, 0.2, 0.3, 0.4, 0.5, then all the way until 1, then 1.2, 1.3, 1.4, 1.5. Obviously, this is going to increase the whole thing to make it longer, right? Now, in order to make the spacing division larger, this is, in other words, increasing the sensitivity, guys, because in order to have larger spacing, I must add more things in between them, right? So from here, this, in other words, is just asking you, how do I improve the sensitivity of the thermometer once again, which you are going to obviously say that you're going to use a larger glass bulb in the thermometer here, right? That obviously improves the sensitivity. And number two, obviously you want to have use a narrower tube in yeah, use an narrower tube in the capillary tube here. Okay, this is just this question here is just another way to ask you about how the sensitivity may be improved, because you want to have more scales in between each and every one of the readings here, right? Then finally, not finally, the second last part here, as a result of the change in tool improving the sensitivity here, what other changes needed to enable the thermometer to be used for the same temperature range? Now today, if I want to have more scales between each of the readings here, obviously what's going to happen is I need to have a longer thermometer, right? Which is the only answer here. I think most of the students should not be able to answer this, but it is what it is. A thermometer must be made longer. Okay, because you want to accommodate more scales here, guys. It's like initially your house could fit 5 people. If you want to fit 10 people here, what should you do to the house? Obviously, you need to have, I mean, in a hypothetical scenario, you need to have larger house, right? But you know, yeah, it's quite a weird question, this one here. I think it confuses a lot of students, but in a way, it exposes you to the different types of ways IGCSEs could be asking you. Okay. And finally, this is a very important concept that you must understand. This last question here, it says that the expansion of a liquid is an example of property that may be used to measure temperature. You know how thermometers work, right? Thermometers is basically using the property that liquid expands when it is heated, right? Then we are using that property to measure temperature change. Right now, this question here, they ask you to state 2 other physical properties that may be used to measure temperature, right? If I want to measure temperature, instead of using expansion of liquid, can I say that the expansion of solid could be used to measure temperature change? This is essentially somewhat how a thermocouple works, right? You are using the metals here, which obviously is going to expand and contract, which gives a reading here, right? So the first other physical property that could use to measure temperature change is going to be the expansion of solids. And as you would have guessed, the final property would have been the expansion of gas instead, right? So there are 3 properties that we could use to measure temperature change. Thermometers use the expansion of liquid to measure temperature change. Thermocouples use the expansion of solid to measure temperature change. Obviously, if you can use liquid and solid, you can use the expansion of gas to measure temperature change as well. And this wraps up the exercises for your homework, right? Anyone got any questions here? Okay. If there is no questions, then let's use the remainder of our 15 minutes to attempt some of the topical questions that I have sent to you guys. Guys, please bring out your exercise booklet, the one that is not with the notes. Let's go through. Can you guys flip to this page here, the start of 2.2? Where is 2.2? Flip. Here. Yeah. Let's go through this question together. Guys, find for 2.2 thermal properties 2017, guys. 2.2 thermal properties 2017. You should end up with this glass bulb looking picture here. Okay, guys, let's attempt this question together with the remainder of our 15 minutes. Anyone cannot find this page? Just flip all the way until you see 2017 2.2 thermal properties. Okay, everyone. You should have been able to find this by now, guys. Yeah, read through this question here and type me your answers in the Zoom chat, guys. I want you guys to start off to give me an answer for this one here first. It's going to be 3 marks, guys. I'm going to give you 5 minutes before I do the question for you as well. Everyone start doing this right now. Oh, very good, Raj. That's a very good answer. Nadia, the level of liquid falls because the heat reaches the glass ball before the liquid causing the glass to expand along liquid drop. Oh, very good, Nadia. That's a very good answer as well. Okay, good. Seems like you guys managed to answer quite nicely. Yeah, let's go through the question together real quick lah. This one here is just going to be a quick one. If you look at this question here, I think you all should know this by now, right? They say that the flask is immersed in a large beaker of very hot water. At first, the level of liquid in the tube falls, but after a short time, it rises. The first part here to ask you, explain why at first the levels of liquid in the glass falls, lah, right? Then you're going to say, Lord, why it falls. I mentioned this, right? As the glass flask is lowered hot water, heat from the liquid expands the glass first, increasing its volume and causing the liquid levels to drop slightly. Okay, this one here will give you your 3 marks where you're supposed to say that the heat expands the glass fast, the volume increases, and the liquid level drops a little bit. Then after that, the second part, they explain why the liquid level tube stops falling and start rising. Right? This is when the heat penetrates through the glass and start expanding the liquid, right? And we know for a fact that liquid expands much more than solid. That's why it rises much more than it falls. Right? So you're basically just supposed to output your knowledge from here. You're supposed to say something like, once the heat penetrates the glass layer, heat liquid in the glass flask goes through expansion. Since liquid expands more than solids, the rise is more than the fall. Something like this. Expansion is not faster, Raj. It's just more because the forces of attraction is much less. Okay, what I mean? The rate is faster. I wouldn't say the rate is faster because there are different things though. Don't use the word rate lah. Just that the expansion is more. Yeah, the expansion is more. Just say that. Okay. Then let me pick another question for you guys to do. Oh wait, let me copy this down here for those that are copying relatively slower. Let me see. This one here. Let's go through this question here right now. All right, last question before we end the day, guys. Guys, 5 minutes, then we'll end the class. Finish this last one. Send me your answers. Oh, very good, Raj. I see you have been paying extra attention in class. Excellent job. But we want to elaborate a little bit more. Like, how do you get the 0 degrees Celsius and how do you get 100 degrees Celsius? Because it's a 4 marks question. You say like, you place it in the melting ice and then put it in boiling water, then you take the reading there, and after that divide it equally into 100 divisions. But yeah, you got the right concept already. Very good. How do I make sure melting ice is 0 degrees? For sure, melting ice is 0 degrees. You just think about it this way: at -1 degree Celsius, the ice would not melt. So it will be like one full ice cube. At 1 degree Celsius, the ice would have fully melted into water already. When will it be 0 degrees Celsius? When the ice is melting. You can see like water droplets beside the ice. That one for sure is going to be 0 degrees Celsius already. Yeah, Nadia, you got the right idea as well. But you missed out the part on how to divide the equal spacings between each other. Yeah, when both are liquid and solid, that is for sure at 0 degrees Celsius melting already. 2020. So the equal space part is used for linear expansion. Yeah, equal spacing is supposed to be for linear expansion. Okay, guys. Last one here. Let's. You could copy this down as a reference point, right? If you look at the mark scheme here, you see what are the main 4 points that they want from you. First and foremost, you're supposed to mention that you're placing it in melting ice, because this here for sure is going to be 0 degrees Celsius mark. Then after that, you could place it in boiling water. In this question here, they say place it above the boiling water steam, right? And then that would be for sure 100 degrees Celsius. If you written down these few things, they will already give you your full 4 marks already. So if I were to structure it, I'll say something like, first, place the thermometer into pure melting ice, this melting ice of pure water. This would allow us to find the 0 degrees Celsius mark. And after that, after that, place the thermometer into boiling of pure water. This would indicate 0 and 100. The rest of this field is divided. Yeah. Okay. Yeah, you could write this down, guys. The most important thing is the keywords here, because this is 4 marks. You must be able to understand what the keywords are and what do they want from you in your IGCSEs. It's always It's always going to be these few things. You have to know the fixed points. You have to know what happens at 0 degrees Celsius. You have to know what happens at 100 degrees Celsius. If you can know that, then just write down all your understanding and all the information down. You should be able to score for all these relatively longer questions. Okay, everyone. Okay, guys, yeah, if you're done copying this, you're free to go. If you have any questions, you're always welcome to stay back to clarify anything you have in your head. If not, then just enjoy the rest of the weekend, boys and girls. Welcome. Bye-bye.
Thank you.
Welcome.